introduce me all the time from that. Thank you so much. Let me just share my screen. There we go. Just put a thumbs up if you can see that. Okay, so thank you so much for the invitation. I promise next time I will definitely come in person. So as you just heard, I was at the University of Leeds until about 6 months ago, and now I'm a joint appointment in Glasgow. I'm half in urban studies in the College of Social Sciences, and I'm 50% in this, I can't remember the abbreviation stands for, embarrassingly, SPHSU. It's a health unit, who are waving at the moment. And most of my work now is taking a slightly different slant, but what I'm going to talk to you about is the technique of individual-based modelling. I'm going to talk a little bit about the work that I have done, the work that I'm starting now in Glasgow. One of the reasons I moved to Glasgow was the setup of a new fantastic programme looking at how these methods can help understand health inequalities. And I'm going to talk about the challenges as well, and sort of come back to this question of, are these sort of models, they take a lot of work, a lot of understanding. Are they really worth it? Do they give us value? I'll come back to that. I have lots of affiliations. Some people collect stamps. I collect affiliations. There's loads. These are my current affiliations. Always happy to collect more. But I should acknowledge colleagues such as Andrew Crooks at Buffalo, Nick Mallison at Leeds as well, who I've done a lot of work with, and the work is here. So just to start off with, this is Trafalgar Square a couple of years ago, pre-pandemic. And what's interesting about this is this was taken around about lunchtime. And who are these people? You know, they're milling around, having a nice time. What are they doing? Why are they there? And where are they going to go afterwards? Now, those questions are kind of the things that I'm really interested in finding out and stitching together. Now, we've got tools at our disposal now to help us do this. We have smartphones, smartwatches, people check into Weibo, Foursquare, etc. So we're starting to get a lot of fine-grained individual information about why people are in a place and where they're going. At the same time, we've also got lots of environmental sensors. So we have footfall counts, car, traffic cameras, environmental pollution cameras as well. So there's lots of different types of data here. And one of the challenges that I'm interested in is, can we get all this data together and link it together? Easier said than done. And then start to answer really complex questions. So Trafalgar Square, centre of London, very busy. One of the highest polluted cities in Europe. If we pedestrianise the centre of London, what impact would that have on an individual's health? And then would their health improve, and would that put less stress on the National Health Service? There are kind of interrelated questions. If we promoted active travel more, so a motion of getting people from driving into walking and cycling, again, what would the impact be on the centre of London, people going to work, the sort of economic benefits, and again, the health benefits? Now, all these sorts of questions are very interrelated. You can't just look at how people move around a city. You have to understand where they're going. You have to understand who they are and why they're going to different places as well. And that really is kind of where urban analytics, the area that I work in mainly, comes from. We're really interested in understanding, using different methods here to explore, understand, and predict cities. What drives cities? Where are cities going in the future? What's the best policies we can do to, for example, be net zero? Glasgow City Council has got a very ambitious target of being completely net zero by 2030. How do they do that? And more importantly, what's the impact of the policies that they may implement going to be on people who live in the city as well? And this is really important for us to get our heads around. When I was at Leeds, I was based in a geography department. Why is geography so difficult? Well, geographical space, the models I build always tend to have an explicit geography in them. We take account of the environment and how people interact with the environment and vice versa. In geography, there are no rules. And the social sciences, this is what makes it I think, much harder than chemistry, physics. They've got like all sets of rules. Newton, Einstein, they've got their rules. We don't have any. The only thing close to a rule we have in geography is Tobler's rule, that everything that's is related to everything else. And if you've got two things that are close by, they're more related than two things that are more distant. Now, current geographical thinking is that maybe with the internet and everyone being so much more connected, and mobile phones, Internet of Things, that's not quite as accurate as it once was. But that's one of the few rules we have. Humans are really tricky to model. Ugh, and human behavior, I'll come back to that. But there's been a lot of thought and a shift in sort of urban studies, geography in the last sort of 10 years headed by Mike Batty, who's at UCL, and David O'Sullivan, this changing thought that instead of looking at systems from as aggregates, so all the populations as one and moving them around, actually let's go from the bottom up. Let's look at the individuals. The idea being that individuals make decisions, and these decisions are the drivers of social systems. For me, this is urban systems and health, but this could be any type of system that we're talking about. And on top of that as well, there's an increasing acknowledgement that these systems are highly complex. Elements are interrelated, there's feedback, there's emergence, things change over time and space. And this is really sort of driving the desire to use these types, of individual-based methods. Now, the one I'm going to be talking about, there's two, but the main one that I've concentrated on is agent-based modeling. Now, if you don't know what an agent-based model is, The Sims is a really nice example. I know, a little dated, but then again, so am I. I'm getting old. It's nice. You create an avatar and you give it attributes, age, sex, education, and you give it a set of behaviors as well. So I'm thirsty, I'll go drink. And then for me, you would then put them into an environment that represents some geography, and you let them move around and do things. And, obviously usually have a research question you're trying to answer, but that's kind of the whole notion of agent-based modeling. The little paperclip here really does age me. This is Mr. Clippy. He is allegedly one of the first agent-based models, and in incarnations of Word many, many years ago, if you start typing in Word, he would just pop up and offer really helpful suggestions. So there you go, Mr. Clippy. Sorry, every time somebody enters the waiting room, it freezes my computer. So as an example here, this is NetLogo from NetLogo of what an agent-based model is. NetLogo is an environment within which you can really easily put together agent-based models. If I'm feeling brave, I'll show you a live example from NetLogo. There's a huge model library. You will waste your afternoon brilliantly going through them, playing with them all. It's fantastic. But here I just wanted to show you that simple rules. In this case, cars moving along a road, slows down, you get a traffic jam. Simple rules, and you get some outcome that you can have a look as well. So simple rules, can they explain phenomena? Microsimulation is something I want to talk about as well, mainly because agent-based modeling and microsimulation, the distinction is starting to become a lot more blurred. There are important differences to me. With a microsimulation, you don't have individuals that interact explicitly, but the two are used interchangeably. Microsimulation is really valuable to know about for two reasons. The first one, it's used increasingly to produce synthetic populations. So the idea that you recreate a population within an area at the individual level. Now, I'm sure in Sweden, same as in the UK, we can't access, unfortunately, individual level data for the entire population. So by using these types of techniques, we can create very accurate level individual populations, which you then can feed into an agent-based model, or we can apply some sets of rules or probabilities to, which is a dynamic microsimulation. So if we want to look at the impact of a policy on an area, on individuals in an area over time, but we're not interested in how people interact, microsimulation would be a better tool. And I'm finding, certainly as we are increasing the levels of data and computational power, that these two techniques are being used more and more together. But I think they do answer different types of questions. So just to give you the population synthesis, I'm going to jump back to this later as well, that in the UK, we get 1% of our UK population we know about. And we also have tables that target constraining data. So for a geographical area, I will know there's a red man and a blue man, or two red men, for example. So I've got the individual, I know 1% of the population, but I also know for an area what the totals should be, how many men, women, how many are ginger and wear glasses, for example. And you run an algorithm, and that outputs all the attributes and all the right people into the right areas. And that simply is microsimulation for generating populations. And for me, I then put them into geographical areas as well, so I can recreate the populations. And as I said, we're starting to use this more and more and attach other attributes in. So work I'm involved with at the moment in Glasgow, we're adding health related variables in there as well to create specific populations to answer the sort of questions we're interested in to do with mental health, physical outcomes, etc., etc. But I'll jump back to that. Back to ABM. It's funny because ABM just seems to be everywhere now. You know, I'm in the social sciences, and it really is kind of a de facto sort of technique, but really it's only what, 20 plus years old. The first sort of real seminal book, I guess, is the Epstein-Axtell Growing Artificial Societies, with the famous adage, if you don't grow it, you don't understand it. Really, really great book. And, you know, I think if I updated this in 2022, there's bound to be loads more books. They're probably ABM for COVID books, so we'll ignore those. But the discipline has rapidly grown over the last sort of 20 years. This is me trying to prove that, you know, ABM's cool. As with most things, the sort of film industry are way ahead of us in terms of and gaming industry, in terms of the graphics and building these agent-based models. Of course, they don't have the issue of having to prove like calibration, validation, their rules, and publish in academic journals. They can produce these really nice simulations, but the sort of technology is everywhere. The Lord of the Rings was one of the first really big sort of simulations where we sort of saw agent-based modeling. It's just so cool. How is it used? Well, this is from 2019, this diagram, and I've deliberately not updated it because I'm going to go into a bit of a COVID rant, just to warn you. But if we look at this one, this is a fairly typical spread of different types of application. So up one scale, we have the spatial scale, whether it's neighborhood up to city level, and across the other axis, we have time, so minutes through to years. Majority of the applications will fall sort of in the sort of bottom left. Most are sort of at neighborhood level, over minutes, hours, days. The migration one's a really interesting one, the Goulden work. Probably more of a spatial interaction model, but you know, that's one of the few examples of using an agent-based model at that sort of scale. Now, if I redid this for 2020 and 2021, it would just be COVID, COVID, COVID. And not all, I'll come to it, not all COVID models are good models. So this is a fairly representative sort of snapshot of pre-COVID ones. So I've kind of already answered why do we need to simulate cities? And I think there has been a shift to looking at agent-based models and a new shift at looking at cities for two reasons. Now, Glasgow, we were fortunate to have COP26 last November. It was October, November time. And part of that came out, you know, cities need to do more to address climate sustainability. There's a very famous UN statistic about more people will live in cities than don't live in cities by 2050, and that's what, 25 years away. So there's that emphasis. So what can we do to improve cities, to make them more carbon neutral, and obviously improve the lives of the people who are living there as well? The second factor, and I guess I can't not do it, I do sign language. This is COVID, the sign language. The second factor is COVID, the impact on that. Now, there's starting to be a huge amount of work and interest on understanding what has been the effect of you know, lockdown for 2 years on cities. And there's one school of thought that says that as soon as we're all allowed back out, we'll all ping back to our pre-pandemic behaviour. But there's also another school of thought saying, well, actually, the system's been disrupted. We can, in a positive way, people can work from home, people are taking different ways of transportation. How can we keep improving, use this disturbance in the system, and actually develop cities in ways and start managing them in ways that are much more efficient? And there's also been another body of work which has been looking at, as we were coming out of lockdown, how do we come out of lockdown safely? Can we use agent-based models to simulate people who are infected and who gets infected and where they get infected as well, and help put mitigation policies in? In the UK, our first of many lockdowns was informed by work at Imperial University, which was a model, I think, based on a Spanish flu, but was updated. So these types of models have really sort of come to the fore as well, and grabbing people's attention. The Washington Post, what was it, March 14th, 2020, the date on there, had a really nice article showing net logo models about how individual based models can be used. And that's kind of precipitates my slight rant about this, where agent-based modeling really caught everyone's attention, because it's a natural paradigm to model individuals and environment and how people move and interact. Of course, for epidemiology, that's a natural use. I went and searched up agent-based models a couple of months ago, and it's literally COVID, COVID, COVID. I'm a journal editor for Computers, Environment, Urban Systems, and about so many COVID articles. And what's frustrating is that so many of them are really not very good. There's no calibration, validation, based on huge amounts of assumptions. And I always have a little bit of a worry when a technique suddenly everybody jumps on a bandwagon that it actually is counterproductive, that instead of working on issues of agent-based modeling, which I'll come on to, where I feel are holding back, people are just producing these simulations that are really not very rigorous. But I'll spare you. If I was there in person, that would be the conversation in the pub. So be lucky for that one. I wanted to show you this. This is, I think this is from Josh Epstein from years ago, so way ahead of his time. And what you're going to see, I think this is bird flu. You're going to see on the West Coast, LA, there's someone with a disease is going to fly in. And then you're going to see how the disease spreads across America. Now, do you think it's going to be from sort of, as you look at your screen, left to right or not? How do you think it's going to spread? Let me just set this off. But it's really interesting because this pertains to be an agent-based model. It is moving. You'll see in a moment, disease spreading. And first of all, it's all the airport hubs. So it's really interesting. Like Atlanta, everybody gets infected, but don't worry. This is a simulation. Everybody gets better. Nobody dies in this simulation. But it's really interesting because I think America was 250 million people, and this is supposed to be an agent-based model simulating disease spread over that period of time. So I just thought it was a really nice sort of example and timely as well. I won't do that one. I'll go with that one. The other nice thing about agent-based models is within scientific reasoning, we have inductive and deductive approaches. If you've read the Epstein book, he talks about it being the third way of doing science, which you can read about it there as well, which I think is a really interesting approach. And I realize it's the Institute of Analytic Sociology that there's a lot of debates going on at the moment about agent-based modeling and theory. Should there be a theory that's specific to agent-based modeling? Can agent-based modeling test theory? And I think this whole sort of, it's not really my area, but it's a really interesting area that I think we're going to start hearing more about as ABM is becoming more established. Now, I noticed on the call, there is, I'm so sorry, I'm going to pronounce your name wrong, Maja Schulte. I use this paper, you should show yourself, I use this paper and recommend this paper so much. Your 2017 paper is brilliant. And it's really nice because it just shows all these different types of behavioral frameworks really well. So I'm very excited to have you on the call. It'd be lovely to meet you at some point. But my gushing aside, one of the appeals of agent-based modeling is this fact that we can create individuals' individual behavior. So we can capture what makes people human. Are humans rational? No. Behavior is also one of the most difficult things to get into an agent-based model. Now, we will never ever model fully everyone's behavior because that would just be madness. Although I did have a call from a guy in Austria who was making a digital twin of the world. 7 billion people, all individuals. So some people want to do this, but you are, as an agent-based modeler, we're only interested in certain types of behavior that we identify that are drivers of a system. Now, working out what those behaviors are is incredibly difficult as well. How do we work out the behaviors? Well, we can look at data. There are other methods which I'll touch on later from AI, which are helping with this, but we will mine the data. But the data is always historical that we use. So we'll set up our agent-based models with data containing past events. If an event we're interested in or a behavior isn't in that data, how does the agent know? How do we know? That aside, there are within ABM loads of behavioral frameworks available now. The 2017 paper, which is one of my favorites, is a great illustration, as well as the ODD protocol. I'm mixed on the ODD protocol. It's a lot of work, but it's useful for making the agents transparent and sort of listing everything down. So if you go and look at somebody else's work, you can understand what they've done and how they've done it. But it's quite hard to do. So human behavior, this is a test that, not a test, that's the wrong word. This is a quiz that I do with my students. Think of one of these numbers, have a think. Keep it to yourself, you can't change either. All right, of the people I can see, put your hands up if you think of number 1. Okay, number 2. one person. Number 3. 1, 2, 3, 4, 5, and number 4. Okay, that's great. You've just fit into my normal distribution perfectly. So this is an exercise from Bill Kennedy, and as I said, humans are really difficult to model, or are they? When Bill has done this on his own students, the response has been majority of people have picked number 3. Very few people pick number 1 or number 4, and a few more pick number 2. So what does that tell me about humans? It tells me there are aspects of our behavior that we can model. People get up, pre-pandemic times, people get up, go to work, multi-purpose trips, come back. Most people have very regular sort of behaviors that we can model. Behavior is something that is hard to model. And if we take the diagram I showed you earlier, so this is exactly the same spatial scale and temporal scale, and we rearrange this now, look at the models in terms of environmental and behavioral complexity. So going up here, simple environments to complicated environments, going along, simple behavior through to complicated behavior. We can see that based on this snapshot from 2019, very few of the models that we looked at actually are complicated. The right and the crime are the 2 models that have both got a complicated environment or more realistic environment and more complex behavior as well. I mean, it would be interesting to repeat this now to take into account what I said about the COVID models, but how this looks now. And agent-based modeling is starting to be used more in public health as well, where they've got fantastic data on behavior as well. So it will be quite interesting to repeat this exercise and see how people are handling behavior. My suspicion is that a lot of the agent-based models still will be not terribly complex in both behavior or the environment, but if you know of any, I would love to know. Am I feeling brave for this? Go on, why not? This is where it goes terribly wrong, and you can tell everybody. One moment. Okay, can you see that? Okay, so far so good. You lot in Glasgow, if this goes wrong, shh. Right, so this is a Schelling model. And this is one of the sort of more famous ones, segregation model. And the idea behind this is that without, Schelling worked all this out using maths, but without this simulation, we wouldn't actually know what the outcome's going to be. So again, simple rules, complex phenomena. So if we set it up, what you see here are orange and blue blobs, and they want to be together. They want to be surrounded by 30% of the same color. So if I run this simulation, we get immediate segregation and clustering in there. Now, if I increase this up and say, all right, we want to be surrounded by approximately 50% of the same sort of person, orange or blue, what would you expect to see? Was it going to be half and half? Well, beauty of simulations, let's have a look. Yeah, sort of quite distinct clusters. Number happy, not doing so happy or not doing so well on happiness. So if we increase this up to, I don't know, let's make, you want to be surrounded by 91% of the same color. What do we think is going to happen? Human nature, nobody's happy. So we can never evolve to a point where we're surrounded by enough of the same people to make us happy. And that's one of the really interesting findings of like using a model like this. I think if you go to around about 75%, you can elicit a situation where everyone's almost happy, but there we go. Let me just switch back out of that. Okay, there we go. I can't believe that worked. Last time I tried that, my computer just blue screened me. To give you some examples of this, so this is some work with my former colleague Nick Mallison, and we developed an agent-based model looking at crime. In this case, we created agents who were burglars. And at the time, Leeds, where the work was set, had one of the most burgled streets in the UK. The reason being it was a student area full of houses that had lots of computers in. It was sort of very attractive. So we worked with the local police organisation to look at why and who were targeting it and what we could do. So part of this was we had interviews from burglars about their motivations for why they wanted to burgle. obviously, because these were burglars who were in prison. These were not the successful burglars, so we caveat that. But we had information about their motivation as well as lots of different types of data. And we used a model called PECS, which is a little bit more complicated than if this, do that. And it's based on physical, emotional, cognitive, and social different factors. So, for example, if a burglar woke up and he needed to eat and didn't have any money, he would go burgle. It's sort of still quite crude, but more complex than we'd seen. Will this work? Oh, it wasn't working earlier. If that did work, you would just see little burglars going around burgling houses. What we did with this is there was an area of Leeds at the time that was undergoing regeneration, and the police were really interested in knowing, if we target harden, secure these houses here and build new houses here, what's going to happen to crime? So we did lots of work with them and showed that how the crime would move and things that they could do as well. And this is a really nice sort of example of descriptive and predictive type uses of agent-based model. So we had theories from environmental criminologists about what would happen. So that was descriptive, what we tested, and then predictive, could we actually simulate using empirical data what's going to happen? Now, there is a debate going on at the moment about whether agent-based models can actually be used for prediction, which is something that I might come back to, or whether, you know, as a tool for prediction, they're just not to be trusted. Oh, my screen. I'm not aware if any of you have had the pleasure of building agent-based models. So I put this in very quickly just to show you the delight that you will enjoy going through this. So the most important part, well, one of the most important parts is the preparation part. There are so many models that I see that you didn't really need an agent-based model to do. So it's, what's the research question? Is this the right sort of technique? What sort of model design you're going to have? So, you know, what sort of behavioral framework are you going to be using? What's the data? How are you going to extract information from the data? What's the order the rules are going to go in, et cetera, et cetera. Verification, testing it out, perhaps in a different coding language, making sure your model's doing what you think it does. And then for me, the two probably most important parts, calibration and validation. And for agent-based models, this is one of the biggest sort of methodological gaps that we have, that because these models are built on individual level data, and you know, there's no two agent-based models the same. There's no large frameworks that you can pick up and adopt. Generally, most people build their own models from the ground up. It means finding standardized calibration validation methods are really, really difficult and really scarce. That calibration validation, and then use the model to do something. I put this one in because I use Java, Python now, a bit of NetLogo, but Julia is one that with the Alan Turing Institute that are starting to develop tools and agent-based models using Julia, which I thought was quite interesting. And then GeoMason, if you're interested in any spatial agent-based models, is a really fantastic framework, which is from George Mason University as well. Repass is, I never got on with Repass, but it's a huge Java based framework as well. And these have varying amounts of just either, you know, you output CSV files through to full graphical interfaces. If you're new to agent-based modeling, I would recommend NetLogo. It's a really nice basic language just to start understanding the basics of what you need to do. There is another book, Crowley told that 2012 one. Oh, so young when I wrote that book. This is part from a book that I wrote with Andrew Crooks, Nick Mallison, Ed Manley a few years ago. And there's lots of stuff online about, you know, how you integrate agent-based models with GIS. So if more spatial based models, but if you are interested, there's some beginner tutorials off this page as well. Okay. Data, which is where I thought we were going next. So one of the biggest challenges, opportunities we've had as social scientists in the last sort of 10 years is that we have so much data at our disposal. I hate the phrase big data, but yeah, it's everywhere. But whilst this creates some huge amounts of opportunities, so remember Trafalgar Square at the beginning, where who are these people, where they're going, what they're doing, how we fit that together. Data can really help us. However, the data is patchy. Often it's not geolocated. We don't know what timestamp is. Ethical issues around some sorts of data, whether we can use them. So while we have tremendous opportunities with all these new types of data, we also have a significant set of challenges as well. And this is where things like machine learning can potentially help us looking for patterns in data, linking data together, helping us data wrangling, the art of checking and making our data robust as well. Within the urban analytics area, you might have heard of Web 2.0, Internet of Things. There's all these new sort of data sources coming online. And one of the most exciting ones is like volunteer geographical information, that you'll see competitions where you get people to go out and collect data or submit data into competitions. And that's great in getting that individual level perspective in, but how you bring all that data together is an issue. One of the I would say, one of the challenges I've now got moving to work in half within public health is there's a lot of longitudinal data, qualitative data. So how do you take that sort of data and translate it into a format that an agent-based model can understand and then make sense of as well? And that's one of the really exciting opportunities here, is that we have all this data, but the challenge is, how do I distill all these different waves of data about people into a model where I can create an agent-based model to see how people, in this case, how their health changes over the course of their life. Switching back to more urban analytics, this, as I said, data is great, unique opportunities, but there's so much work still to be done on trying to extract behavior from these types of data, because someone's behavior changes over space and time, and you may have a handle on the behavior, but an individual may have an interaction and that changes their behavior completely. Plus, if you're interested in routine behavior, if you're what number you pick between 1 and 4, fine. However, if you're interested in more extreme behaviors, or things like what happens if there's a global pandemic, models couldn't handle that 2 years ago because we had no data. So how do we introduce behaviors in that the system doesn't know? That's one of the things we're interested in as well. So data, I won't spend too long on this, is no surprise to you for individual-based models. Data, I think, akin to any sort of modeling technique, really is sort of crucial. There are lots, especially around sociology, there's a lot of conceptual models and almost thought experiment models, which are really valuable. But within the area I work in, I need data at every stage. I need to understand the city, I need to understand individuals, I need data to be able to calibrate, to validate, and this data is about mobility, behavior, everything. I'll come back onto this one in a second. I thought I'd give you an example of some data. So this is some work from one of my PhD students a couple of years ago, and we had this huge amount of smart card data. This is Shenzhen in China, just sort of north of Hong Kong. And we have lots of data about how people check in and out on metro. So transportation data is a hugely rich data set, because you've got time and place stamps and all the data. So we went through looking at different types of smart card data, where people went. We reclassified some of the data. So when people left the metro station, they would check into Weibo, and we sort of classified the different types of places. So we got an understanding of that sort of last mile problem. Where are people going? And then don't worry about interpreting the graphs. Then we sort of had a look at, on a daily basis, different groups of people, where they're going, or what they're doing. What's interesting, it kind of shed a little bit of light on what's happening here. I don't know if you can see my cursor actually, but on the Friday one, you can, great. If you look at the green line on education, this is students. So they leave, they go somewhere, but then around about 6 o'clock in the evening, we worked out that instead of being education, the leisure line increased up, and we kind of, this is students we're looking at here. So students left university and went to the pub on a Friday evening, which is horrific. But that sort of behavior is kind of easy to validate. You can pick out different patterns of behavior and say, oh, actually, we've kind of got the groups right and we've got the activities right. And yes, it's no surprise students go to the pub on a Friday. I'd be surprised if it was just Friday. This is an example of how you can get it wrong. So this is work of my colleague Nick, and he won't mind me laughing about this on his behalf. But I was involved in this, and we wanted to understand how people moved around a town. And this particular town had lots of cameras put around it to collect information on people moving by. So we knew how many people were moving through this town, different parts during the day. We didn't know who they were or where they were going. We just had these captures of amounts. So we used the UK census to create a population using microsimulation, turned it into an agent-based model. In the UK, we have these time work surveys. So we had a look at that and attached information to the population about, who's going to work, who's going to school, etc., etc. Put them into houses and, fairly confident, let's go. We've won this, it's brilliant. And the results I'll talk you through weren't quite that. So we used just all quantitative data sets to build the model. Now, the real data is this thick back line. And that is sort of like aggregate total, what people are doing over the day. So we should be close to this line. Let me just move that. So what we found, the first one, so the dotted line here were the first results. And we kind of got people going to work fine. Then this drop in the middle of a day. What happens in this town at 10 o'clock? Why haven't we captured it? And this town had a science cafe, and I went and spoke at the science cafe. And it turned out at 10 o'clock, more people are about because it was the retired people were going off to the local supermarkets and the local cafes. And we just hadn't accounted for that because they weren't in the data we were given. So put those people into the data, ran the model again, and this dash line here, which is more in tune with what was actually happening. So the lesson for us there was that as computer scientists, we really can't just stay in our ivory tower. We have to go talk to people. And that qualitative data is incredibly important because without talking to people and really understanding what's happening in a place, how can we possibly aim to simulate it? So we were a bit humbled by that one, but it's quite a nice example of when things go wrong. How am I doing it on time? Because I've no idea of, should I keep going? Keep going? Okay, I'm pacing myself. This is an example, I'm getting close to the end now, so hang with me, from Andrew Crooks. And this was, about 10 years ago. So again, pre-pandemic, but what I like about this, it's a really nice model. It uses lots of different types of data and attempts to use social networks as well. So here he was looking at how disease cholera spread around refugee camps in, I think, Kenya it is as well. Made a very simple agent-based model, had people moving around, sort of like a routine. I don't think there's any explicit behavioral frameworks in here as well. Moved them around, but also developed a very simple SEIR model, which I guess we're all pretty familiar with now, and linked that to the environment as well and into their routine. So where they might come in contact with infected individuals and water sources. There we go. Ran a whole different types of simulation over different space and time, so different locations, and had a look at a variety of patterns. So it's almost like an ensemble model that he ran lots of different simulations and tried to get an idea of the uncertainty with this. What's the most likely situation going to happen in this particular example? Oh, jumped off it. So I like this one. I've taken out a slide, but you also linked in agents as well. So for each person in different camps, they had groups that they linked to and saw on a regular basis. And through that, they were able also to sort of look at how the disease spread throughout the populations. And it's really interesting how that model works. I think it's open source as well, but quite a nice disease model. This is, I wanted to show you, talking about data. So crowdsourced data is, like Twitter data, particularly, well, less so Twitter data now. You can't scrape it anymore. Maybe Elon Musk will allow us to collect it again. But this is from a few years ago. This is Sarah Wise, who's down at UCL, and she looked at wildfires, particularly using how can you use this sort of crowdsourced data when events happening, a natural disaster, to inform the model as the model is running, and therefore help sort of local government practitioners as well. Really interesting. I want to jump back, since we're sort of roughly in the area of data, to populations. So one of the biggest challenges we have is getting the right sort of data. Now, anyone who has been involved in a research grant, say it's a 3-year grant, and you need access to a really sensitive data set, you'll probably spend 2 years trying to get access to the data, if that happens. One way we might be able to sidestep this is by creating synthetic versions of very sensitive data sets. So I have a project with the Alan Turing Institute in London, QUIP, and it's all about looking at In this case, health records. Can we take health records, so very confidential for a reason, but can we synthesize a data set with health records in, keep all the information in there and the relationships that as a researcher I'd be interested in, but preserve the people's anonymity, so keep privacy at the top of the agenda as well. So that's a project that's ongoing at the moment with a London hospital. But if that's successful, and we're using a whole range of different deep learning methods to do that, if we can synthesize really sensitive data sets, it would be fantastic, because then you could produce financial records, all different types of sensitive data sets, synthetic versions of them, but ones that are really usable for us as well, and turn into ABMs, run dynamic microsimulations, whatever we're interested in. So that I think that type of work we're going to start seeing a lot more of, because the issues with privacy, obviously, are understandable. We can't access that type of data, but as researchers and using these types of models, we do need individual level rich data. So where does all this go? Well, this sort of whole work I've talked about, and I appreciate I've kind of jumped around a bit, is all moving toward one direction, and that's looking at digital twins. In the UK, actually, I read an article, I was reading a paper earlier this week, which referred to them as digital shadows, which I quite like. So in this context, a digital twin is, can I recreate a city, Glasgow, Leeds, inside my computer? Can I recreate the environment, the people, all the processes that go in there? Now, obviously, that's a really attractive idea to like governments and policymakers, because if you've got a fully accurate digital representation of your city, you can then say, oh, what happens if I do pedestrianize? You know, what happens if in Glasgow there's this horrible motorway through the city, the M8? What if we get rid of the M8 and, you know, turn it into green space? What's the impact going to be? So it's a really attractive tool. The Alan Turing Institute has been, through the pandemic, we've been involved in work building digital twins at a crude level to simulate COVID spread throughout populations. And that's kind of a sort of basis of the work that I'm starting to do at Glasgow. Now, I only joined Glasgow a few months ago, but one of the things that we're really interested in both sides of my job, both in urban studies and the health side of my job, is can we create digital twins that are going to be useful for both sustainability and for health? Now, I wanted to draw a picture of this. These are questions that we can potentially ask with them, but I'm going to use my hands instead, because I'm rubbish at drawing diagrams. So part of the work is going to be at a very small scale, individuals. Can we sort of use health data, longitudinal data, and create an idea of people's lives and how the choices people make affect their future health? But can we also scale that up here to a city level, where perhaps behavior isn't as complex, but can we understand how policies from a local council or government impact on people at this level, but also trickle down to their behavior down here as well? So it's kind of a digital twin on a couple of levels. For me, this links both sides of my jobs in, because I'm interested in understanding the impact of health, impact of sustainability policies on health. So I can build a model of a city, and then I can link into the health and sort of say, okay, if Glasgow implement this policy, what's going to be the impact on health of people in the city? Will it widen inequalities, or will it narrow inequalities? And there's also this notion of what are the unseen consequences? If we gentrify all the houses in poor parts of Glasgow, does that mean local people are pulled out of those houses because they can't afford them anymore and have to move elsewhere? You know, what's the impact of active travel? This 15-minute city, does it work? Is it beneficial? There's lots and lots of questions that we can sort of begin to get to ask with that. Now, public health, I'm glad there's some public health people on the call. One of the reasons I'm looking at public health is because, and this is my take on it, is that from my view, public health people sort of go, more sunshine, people's health gets better, great relationship, that works really, really well. I would go, look, real sunshine, it doesn't look like people's health gets better, because when people go out in the sunshine, they drink beer and they eat donuts and things like that. There isn't that direct relationship. And I find that my take with public health, and I think the role that I can play in this area, is that public health is a very reductionist approach. It strips away all the complexity of a problem without dealing with it. And these approaches, agent-based models, microsimulation, are called system science approaches. And they sort of put that back in there. So it's really interesting. Public health is definitely moving to this area, and they've got this great data, these fantastic problems that, not fantastic, wicked problems that need solving. But there's a real shift in the approaches that we're taking, and that really sort of forms a lot of work I'm doing at Glasgow. And I wanted to sort of, because I've talked about work I'm about to do, this is a project that is ongoing, and this is using microsimulation. And this is a Cypher project, which is ran out of Glasgow. And we're looking at impacts of early interventions on health. And at the moment, we've created a population for the whole of the UK, but here's some shot with Glasgow in there as well. And we've used that to build a dynamic model. So people are interacting, there's individuals, and we're interested, at the moment, looking at, do people's mental health improve if we give them more money, more living wage? What actually happens? And this, it's hugely complicated because you have to involve health economics people in, mental health specialists, construct different system maps and DAGs and causal loops, and embed all that into a model to try and understand what's going on. So that's a project that is ongoing at the moment. There's a website for it as well, and a really interesting project. How am I doing on time? Because again, I could keep going. I've been going for, I will round up soon. So this slide, this amused me. I gave a talk last year, might not amuse you, and I came up with Heppenstall's law that when a technique reaches maturity and acceptance, all these navel-gazing papers start appearing with things like key challenges, future developments, etc., etc. And that has been the case with agent-based models. Now, I'm guilty of this myself, as you can see. But what's interesting is that the 2008 paper by Andrew Crooks listed all the problems with agent-based models that we need to solve. I co-wrote a paper with Andrew, I think it's 2021, I can't remember. All bar one of those issues are still there. So what's going on? Why haven't we solved all these issues of agent-based modeling? Hang on, my computer froze again. And these ones, this is a paper by Steve Manson, which quite nicely sort of summarizes all the big methodological issues, behavior, validation, understanding complex results, and how do we abstract, how do we scale up from small scale here? If I model a street and all the processes there, then I want to model a city. What are the processes here that I have to model up here? Really tricky. Calibration and validation, I will give a moment to. In my opinion, if you can do research which solves calibration and validation agent-based modeling, you will be given a Nobel Prize in something, because nobody does it. Really, really difficult. How do we evaluate behavior? Do you do it by pattern? Do you well, hopefully not just an R-square, but how do we do this? When we build these models, really complicated of space and time patterns, what are you actually evaluating on? How do you know your model is a success? Does anybody ever do any uncertainty quantification? Because in building these models, you have uncertainty in your data, you have uncertainty in your rule construction, you have uncertainty in the order that the rules go in, etc., etc. People don't really quantify that and then communicate to a stakeholder. In this situation, you do this, I'm 80% certain this is what's going to happen, and this is where I'm uncertain. And that's a massive issue in agent-based modeling, and a reason I don't think that we see a huge amount of agent-based models translating into policy as well. Some of the work I'm still doing with Leeds University is the idea of can we throw data into a simulation as it's moving? So dynamic data simulation. And the idea here is that this is the real world, this is your model. As soon as you start doing your model, the real world and your model output go apart and it diverge. And if you add data in, they'll snap back. So can we use this approach to do really accurate short-term forecasts? So the classic example, if somebody blew up, I don't know, Glasgow Central Station, God forbid, people will start texting, sending information in. So could we run a model in real time, understanding what's happening there and then to help manage a city? A lot harder than it seems. We built, I'll just show you this quickly. So there's a couple of papers there on it. But we built, this is what we've been working with, a prototype train station, really, really simple, just to try and get our heads around it, and using things like particle filters. So methods from physics and mathematics to try and build these types of models. But I'm happy to talk about those a different time. This is some of my more favorite work at the moment, this uncertainty quantification. So taking methods from sort of engineering and maths, where, and meteorology, where meteorologists do weather forecasts and say tomorrow there's a high chance of it raining, and you get some idea of uncertainty. So can we take those sort of methods from meteorology where they give you an idea of uncertainty and apply that to social systems? And this is what we're starting to do here using, again, I won't go into history matching and Bayesian computation and linking them together. The idea being that, can we sort of understand where the plausible space is, ignore the rest, and that will give us an idea of where our parameters are likely to be, but where the uncertainty is as well. Again, there's a paper there that's just been published. Now, I spoke about behavior, and behavior being a bit of a pain. So what if, the data, if it doesn't contain what we're interested in, what if we just got rid of all the data and don't bother with data? Build a model, a representative model. We know that, individuals, but instead of giving them behavior rules, what if we just let them learn? And that's sort of been the idea through reinforcement learning. Put the agents in a simulation, let them start learning. So this is a thing I stole from Ed Manley, this slide. So here on one side, you can guess one of them is being trained and rewarded to go through the 2 dots. The other one is a bit like me first thing in the morning, looking for the coffee pot. It hasn't been trained and hasn't been rewarded. Now, there's a lot of work going on at the moment, and I've got work within my group where we're starting to look at reinforcement learning as a way, can complex human behaviors such as burglary, motivations behind burglary, migration, be learned through reinforcement learning? So no data, just we'll let them learn the behaviors and see what happens. It's interesting. So sort of coming to the end, there's a gold star for anyone who understands why I put the Snow Crash novel book in there as well and has read it. The sort of work I'm involved in is really all about understanding what's a city like now, what are the processes that drive a city now, but from the bottom up. There's loads of reasons, I've sort of spoken about COVID, health impacts, sustainability. These are massive issues that are not going to go away. And cities have a huge amount to contribute in terms of reducing inequalities, improving sustainability as we go forward. Trying to model them, however, is a bit of a headache. I think agent-based models have an awful lot to offer, but there's also an awful lot of challenges, unique challenges with agent-based models that we need to overstep as well. So can we look at other disciplines and sort of work out what works there, like, for example, ensemble modeling in meteorology, ABC work, and quantification certainty from engineering? Can we steal those methods, bolt them into our ABMs for social systems? I put collaborative model building. I think this is an issue in agent-based modeling. Our models are so different and unique. There are sites where you can go put your model code, but we still don't have, we're still working very much in our own silos. Ecologists are really great at some behaviors. I'm a spatial agent-based model. I'm really good at handling space. We need more communication as well. Is this my last question? No. Yeah. So what about the role of machine learning as well? This is not something I've really spoken about, but again, we hear machine learning has become such an umbrella term now as well. And we started to look at sort of deep neural networks to extract behavior. Reinforcement learning is becoming more prevalent. DDA, data simulation for real-time simulations, are all starting to come online. But where does that go into the future? There's a little Meta, is that right? Facebook Meta, that we're all going to be virtual online. Unity, we're using the Unity platform. I'll see if I get this running for you, for work to recreate environments and put our agents within them as well. You extend this, say, in 10 years' time, will we all be sat in a classroom with our, at home with our VR goggles on, interacting with each other? Meta would have us, that's the way it's going, but agent-based models would be the perfect way to power these types of systems as well. Virtual reality, and I think Paul Torrens at New York State is doing an awful lot of work within the sort of virtual reality zone as well. That's the book that I wrote. Oh, my screen froze again because somebody's come in. So the question, agent-based modeling, is it worth it? What I should have probably said right at the beginning is it's a rhetorical question, or it's a question I'm going to ask you. Do you think it's worth it, the effort? Over to you. Thank you very much.
Thank you very much. Of course, it is worth it. So I have an easy answer. Thank you very much for this really fascinating talk. It was really amazing. A lot of very cool stuff, and we learned a lot from you. Thank you very much, and congratulations to this work that has gone so many different areas. And now I think I will stop the recording so people can feel comfortable to also show up on the camera and ask the questions.